Now let us look at electric field intensity or electric field strength. You can see it's also a vector quantity because it has a bar on top. And it's easy, it's better we start by defining it. So maybe we can say it can be defined as, so it can be defined as force per unit charge, force per unit charge placed in electric field. It can be defined as force per unit charge placed in electric field. So maybe you can represent it as IA, say that E bar is the same as force per unit charge. So that is what we have as our electric field intensity. Now maybe we can say consider a charge point, a point charge Q1 at the origin, if another point charge Q2 is placed in the vicinity of Q1 then Q2 is acted upon by a force, according to Coulomb's law, it is acted upon by a force according to Coulomb's law as like so, AR12 bar, or you can just say AR2, it's okay. So let us call this as equation 1. Now from our definition, we are saying that electric field strength is defined as force per unit charge placed in electric field. So now if we divide actually this force by a charge, then we are going to have F2 bar all over Q2 to be the same as Q1 over 4 pi epsilon naught R12 squared AR12 bar. So you can call that as our equation number 2. So from our equation 2, so say from equation 2, F2 bar all over Q2 bar is denoted as E bar, which is electric field. strength. It is electric field strength. So then if that becomes that, and we can say that thus maybe E bar will be the same as Q1 all over 4 pi epsilon naught R12 squared AR12 bar. Let me say in general, E bar is the same as Q over 4 pi epsilon naught R squared AR bar. This is the general equation for electric field strength. And since we are saying that electric field strength is force per charge, the units must be newtons per coulombs. So call that as our equation number 4. So that is our equation 4 for our electric field strength. So maybe we can say where R is the distance from the point charge, to the point where the intensity is to be computed. Distance from the point charge to the point where the intensity is to be computed. And then AR bar is the unit vector along the direction joining the two points under consideration. Joining the 2 points under consideration. Now that is how we have that. Now if we have more than a single point charge, or we have several point charges, then let us see how we can compute that. So then we can say for n point charges, somewhere there say maybe for n point charges, Q1, Q2, say Q3, all the way up to Qn. For n point charges, Q1, Q2, all the way up to Qn. Electric field intensity is derived using superposition principle. So maybe I can say thus E bar will be E1 bar, E2 bar, E3 bar plus En bar. Now from there then we can say, because we have n point charges, then we'll have Q1 all over 4 pi epsilon naught R1 squared A R1 bar plus Q2 4 pi epsilon naught R2 squared A R2 bar plus Q3 over 4 pi epsilon naught R3 squared A R3 bar, say plus all the way up to Qn all over 4 pi epsilon naught Rn squared Arn bar. That is what we are going to have. And again, if we factor out the common term in our equation, then we'll have 1 over 4 pi epsilon naught. That is a common term. Then the summation from k is equals to 1 to infinity of qk all over rk squared ark bar. So this is what gives us our field intensity, that, and that gives us our equation number 4 as being that. Now we can still have the same equation representing position vectors. So say similarly in terms of position vectors, we are saying that similarly in terms of position vectors. Now in terms of position vectors, we can say that our E bar will be represented as Q1 all over 4 pi epsilon naught R bar minus R1 bar cubic R bar plus Q2 all over 4 pi epsilon naught R bar R2 bar cubic R bar R2 bar plus say Q3 all over 4 pi epsilon naught like so, say plus Qn like so. That is how we represent our vector in terms of position vectors. I mean our electric field intensity in terms of position vectors. So again, if we look at our common term here, we're going to have 1 over 4 pi epsilon naught as being our common term. The summation from k is equals to 1 to infinity of q k all over r bar minus rk bar cubic into r bar minus rk bar like so, and that becomes our equation number 5. That will give us our equation number 5. So maybe we can again look at an example related to electric field strength and see how we can be able to answer that kind of equation. So now we have our example here related to electric field strength. So we are saying that point charges of 3 times 10 to the power of 3, just a minute, 3 times 10 to the power 3 microcoulomb are placed at each of the 3 corners of a square whose side is 0.2 meters. Then you are told to find the magnitude and direction of the electric field strength at the vacant corner point of the square. So now it's good that we have a drawing of this question actually to represent all the forces, all the charges, and see how the electric field strength are acting upon it. So let's try to draw a square. So we have that. Let us assume that that is the vacant corner. Say that this corner is Q1, that be Q2, and this be Q3. So we want to get our electric field strength at the vacant corner. So say that that is that, the particular length, this be that, and this has to be the diagonal of the square. The distance here will be the diagonal of this square of ours. So we have that, and we have that. Maybe say that, so due to this point, due to Q3, the electric field strength will be E3 bar. Due to Q1, the electric field strength will be E1 bar, and due to Q2, the electric field strength will be E2 bar. This is a very good example of a superposition theorem that we want to apply. Yeah? So we are saying that now the electric field strength E at that vacant corner E bar must be E1 bar plus E2 bar plus E3 bar. And again, we've been given the lengths or the sides of the square. So this side is 0.2 meters, and this side is also 0.2 meters. So we need to compute this side also, yeah, so that we can get the value. This is R1, and this other one, due to Q2, let us call it as R2. Due to this, call it as R3. So as a vector, we can have the bars on top also. So say that this will be given as E1, which is the same as Q1, all over 4 pi epsilon naught R1 squared A R1 bar plus Q2 all over 4 pi epsilon naught R2 squared A R2 bar plus Q3 all over 4 pi epsilon naught R3 squared A R3 bar. Like that. Again, if you are very keen, if you assume that this is also a Cartesian coordinate system, and the vertical axis is our y-axis, the horizontal axis is our x-axis, then we are able to see that the electric field strength due to Q1 is along the x-axis. So this unit vector can just be represented as AX, and the one along the what? The vertical axis, which is E3 bar, is along the y-axis. So this unit vector again can be represented as AY bar. So if we were to write that, and before that maybe E2 has to be resolved along the x and along the what? Y-axis. Now, if that be the case, then if this is a square, then this angle must be, because this is cutting the 90 angle at the center, this must be 45 degrees, which similarly to that, which is also what? 45 degrees. So then we can resolve our E2 along the x and the y axis. So if we resolve that along the x and the y axis, we can have our values for this. So this, we can just have this as being still Q1 over 4 pi epsilon naught R1 squared. Now instead of AR1, because it's along the x-axis, this value will just be AX bar plus Q2 all over 4 pi epsilon naught R2 squared. This one has two components, so let us still retain that. Then plus Q3 over 4 pi epsilon naught R3 squared in the direction of AY bar. So now let us go to our question now. Again, one thing that we also need to find out before proceeding further is the value of R2. Sorry, this should be R3. So R2 as a magnitude, which is the distance from this point to the vacant point, must be the root of 0.2 squared plus 0.2 squared. And that, if you punch with your calculator, you'll find that root to be the same as 0.2883 meters. So we have our distance here as being 0.283. We have meters. So now let us go back to, now let us solve our question now. So let us get E1. So E1 must be what? That remember these values are in micro. Charge is 3.0 times 10 to power 3 micro. So instead of that, we'll have 3 times 10 to power 3. Micro means is 10 to power negative 6. 10 to power negative 6 all over 4 pi epsilon is 10 to power negative 9 over 36 pi times r squared, and my r squared there is 0.2 squared. The unit vector is AX bar. Yeah. So if we simplify that, I'll have 10 to power negative 9, another 10 to power negative 9, so they will cancel. That and that goes, I'll have 9 times 3. Yeah, 9 times 3 all over 0.2 squared AX bar. That will translate into is 674.08 AX bar. Now the units, we had said that these can be given as newtons per coulombs, or it can be volts per meter. Those are the two units that we normally represent electric field strength. Then now the second one, we need to look at our electric field strength E2, which we are saying that has two components along the x-axis and along the y-axis. Because you see, at this point, you can never tell whether it is along this x or y. So we need to resolve it by representing E2 with a cosine of the angle so that it is along the axis, the x-axis, and again E2 multiplied by the sine so that we get the component that is along the y-axis. So we can say that, let us start with the x component. The x component of E2 bar, the x component of E2 bar is the same as the magnitude of E2. So we resolve it along the x-axis. So it is the magnitude of E2, the cosine of 45 degrees. So that magnitude of E2 will be Q2. Yeah, and Q2 again is 3 multiplied by 10 to the power of 3 times 10 to power negative 6 times 10 to power negative 6 all over 4 pi times 10 to power negative 9 over 36 pi multiplied by the radius. See, it's here, the radius R2, and our radius R2 is given as 0.283 squared, 0.283 squared, and this translates, if we try to simplify that, you are going to get 336.67 as our magnitude. 336.67 being our magnitude. So that now, if we solve our value so that we get our E2 along the x-axis or the x component, so I'll call that as E2x so that it is the x component. That will be 336.67, sorry. Now the cosine of what? 45 degrees in the AX direction. Now it's no longer AR as we used to have it. Now it is AX direction. Now that value in that particular direction is going to be 238.06 in the AX direction. Now similarly, if we resolve the same component along the y-axis, we are going to have, maybe you can say, the y component of E2 bar must be the magnitude of E2, the sine of 45 degrees. So we are saying that that y component, the magnitude is the same magnitude as what we found here, which was 336.67. So that value here, we are going to have it as being what? E2y bar will be 336.67, the sine of 45 degrees. And remember, sine 45 and cos 45 is the same thing. And so this also gives you what? 238.06 of a what? Y bar as the unit vector. Now at least we found that, or rather than hence, maybe I can conclude that here, that hence A2 becomes what? Hence, my E2 bar will be 238.06 AX plus 238.06 of what? AY. So now that is our E2. Then finally we can also get our what? E3, which is common. It's along the what? AY direction, yeah? So that becomes what? E3 and E1 must have the same magnitude, but the difference is the direction. So we can say that our E3 bar will be the same as Q, which was 3 times 10 to power 3 times 10 to power negative 6 times again 10 to power negative 6. That is our Q all over 4 pi epsilon 10 to power negative 9 over 36 pi times the distance, and the distance is 0.2 squared. Then the direction here is AY bar. So the value is the same as the other value, and you're saying that this value should be 674.08 in the direction of AY. So then we add all our values so that we get the final electric field strength. So if we add our values, we don't need our drawing. So we can say thus E bar must be E1 plus E2 plus E3 bar, and this is 674.08 of AX. Then my E2 must be 238.06 AX plus again 238.06 AY bar, then plus 674.08 of AY bar. Now when you add vectors, you must add the same unit vectors together. So if I add the ones with AX together with another one AX, I'm going to have what as my final vector? 912.14 AX plus 912.14 of what? AY. Now this becomes my unit vector E bar. My unit vector E bar. But you see, our question was asking us to get the magnitude of that particular unit vector. Now for me to get my magnitude of E bar, then I need to compute this 912.14 squared plus 912.14 squared, and that will give me 12898.96 volts per meter. That is what we are going to get. And if I was to sketch this, now the electric field intensity at the vacant point, because this is the direction, then I'll have my sketch as simply as, assuming that this is a square, yeah. So my sketch, I have electric field strength in the y-axis, which is 9112.14 AY bar, and another one in the x-axis, which is again 9112.14 AX bar. Then we have that, because they are the same whatever electric field strength, they have the same magnitude, then this must be at the center, which gives you what? 1298.96. 96. That is the direction. So it's in between the two electric field strength. This was my Q1, that was Q2, that is my Q3. And so that is our question, and now we can answer that. So then maybe next time in our lesson, we are going to look at electric field strength due to continuous charge density. We've been looking at charges due to static charges or point charges, but next time we look at electric field strength due to continuous charge density. We are also going to look at electric flux density and the next law. You see, we've dwelt so much on Coulomb's law, but next time we are also going to look at Gauss' law. Thank you.